Now, moving right along to the more of this chapter. We learned in this chapter, in chapter 3, about, well, chapter 2, about the idea of isotopes, mass number, and atomic number. Our atomic number was a fancy way of looking at the proton count. The atomic number is entirely responsible for our elemental identity. If we don't have the right proton count, we don't have the element. So this was kind of an issue dealt with when we had alchemists. They were trying to turn lead into gold. Well, they didn't have the tools they needed to turn lead into gold. They would have had to strip away so many protons, actually, to convert a molecule of lead to a molecule of gold, or atom of lead to an atom of gold. And second semester, we get into nuclear chemistry, which involves transmutation, which is a way to turn one element into another. When the nucleus starts reacting and loses a proton or gains a proton, it can become a new element, and it often does. However, the majority of chemistry deals with electron chemistry and not nuclear chemistry, and so all compounds stay the same element, keep the same elemental properties. Mass number was the proton and neutron count. If I reported something, I'd say boron, say 511. What this means is boron would have 5 protons, and the mass number is made up of, and the 11 is made up of 5 protons plus 6 neutrons, because the total mass was the sum of those two numbers. Now, the number that gets given in the periodic table deals with the average atomic mass, a weighted average of the atomic mass, so that we don't report 11 in the periodic table. For boron, it's like 10.8, I think. 10.8 something, because while boron 11 is the most common type, there is a boron 10. So the average atomic mass of boron in the periodic table is 10.81, meaning that there is some amount of boron 11 and there's some amount of boron 10. If we figure out the average mass, you would get 10.81. Which brings us to isotopes. Isotopes are when the one element has a different mass number than its twin. Essentially, that boron 10 and boron 11 are isotopes of boron. They have all of boron's normal properties, just one is slightly heavier. And this will play a part in some reactions where weight makes a difference. But for the most part, boron 11 and boron 10 will have almost identical properties. Carbon 12, carbon 13, and carbon 14 will all have similar carbon-based properties. It just carbon 13 is slightly heavier when it comes to certain things. Hydrogen 1, hydrogen 2, which is deuterium, hydrogen 3, which is tritium, all will do hydrogen-type reactions, but reactions that require speed and think about the mass, that this one's twice as heavy and this one's 3 times as heavy. These often react a little bit slower because they're a little bit heavier, a little bit bigger. But these are all isotopes of hydrogen. So you need to be able to recognize an isotope, recognize a mass number, be able to figure out how many neutrons are there based on the atomic number and the mass number. In this case, hydrogen, 1 proton, 0 neutrons. 1 proton, 1 neutron, and 1 proton and 2 neutrons. And those are going to relate to different reactions, different things. Isotopes and isotopic abundance. How would we actually determine isotopic abundance? It's actually not too hard. It seems difficult, and especially it's very difficult for what we learned right off the bat. But early on, but now that we've gone through all of our material, it's not so hard. So for example, it is simply, we take, to get the isotopic mass, the weighted average, we're going to take the isotope mass times the percent, and we're just going to take the sum of all those numbers. The isotope masses times their percent. So for chlorine has chlorine 35, which is 75%. This is a rough rounding. And chlorine 37, which is about 25%. If I took the average right there, so I would say 35 times 0.75 plus 37 times 0.25, we added those things together. 35 times 0.75 is 26.25. 37 times 25% is 9.25. I add those together, 26.25 and 9.25, and what do I get? I get 35.5. Now, what is the actual atomic mass or weighted average for chlorine? It's 35.45 something. So that's not a perfect atomic mass, and that's not the perfect isotopic abundance, but it's close enough to get us within the range. Now, you may or may not have to do this, but at this point, this should seem simple compared to all the craziness we've had this semester.